Here we are at the end of the semester. Let's reflect briefly on some mysteries of the physical universe. Admittedly, these are not ideas that you will use practically, but they should enrich your mind and cause you to wonder at least a little bit about the physical world and, of course, the one who created it. We're reminded in Job that God's ways, which include his creative physical world, are great and mysterious. Job 11:7 says, "Can you fathom the mysteries of God? Can you probe the limits of the Almighty?" Well, we will look at four mysteries of the physical universe. And by mysteries, I mean things that are not intuitively understandable. And believe me, there could be more, but we'll limit ourselves to four. And those four you can see in front of you are the idea that time depends on gravity. The second one is this idea that the speed of light is a universal constant. Third is the notion that light and matter both have dual natures. And fourth is this especially intriguing notion that's called quantum entanglement and non-locality. Well, first is gravity's effect on time. Now, we discussed this earlier in the semester. We saw that time slows down in the presence of gravity. The greater the gravity, the slower time runs. And in the extreme case of a very strong gravity, such as that associated with black holes, time can actually stop. How is that possible? How can time even slow down, much less stop? It's very weird and very strange. A second mystery is the idea that the speed of light is constant to all observers. Now that sounds simple enough, but let's look a little deeper. The diagram shows two flashlights. One is mounted on a moving rocket ship, and one is fastened to a table that is on the ground. Now you might think the person that's standing on the ground and not moving would measure the speed of light from the flashlight on the rocket ship to be more than that of light coming from the flashlight on the table. This person would see, you would think, light from the rocket flashlight to have a speed that is that of the rocket moving plus the regular speed of light, whereas the light from the table would just be the regular speed of light. But when the measurement is made, the person on the ground sees identical speeds for each situation. This idea that the speed of light is a universal constant forms one of two starting assumptions to Einstein's special theory of relativity. And results derived from this theory have been verified many times, so it seems that the universe has this mysterious feature built into it. A third mystery is something we have looked at later in the semester. It's the idea that both light and matter behave as if they have wave and particle-like properties. And of course, the wave features of matter become much more apparent as matter is reduced to very small size, i.e. what we call the quantum world. A wave gives out energy gradually, whereas a particle, like a bullet, delivers it all at once in discrete, irreducible portions. So which is it? Wave or particle? Is light a wave or a particle? Is matter a wave or a particle? It doesn't seem like it could be both, but actually it depends on the type of experiment being done. Sometimes light behaves like a wave, sometimes like a particle, and the same for matter. Sometimes it behaves like a wave and sometimes like a particle. That is very strange and weird indeed. Now the fourth mystery is something we have not discussed in class and is in a sense the biggest mystery of all. It's called quantum entanglement and non-locality. Now what is this all about? Well, let's use the analogy of twin sisters. The first twin leaves her place of birth and heads off to the right. When anyone asks her if she likes ice cream, she answers yes, because she loves ice cream. Unfortunately, the two twins are separate, and so the second twin goes to the left. It turns out the second twin does not like ice cream, so when anyone asks her, "Do you like ice cream?" the answer is always going to be no. But on occasion, these two twins, even though separated by long distances, could be asked at the same time if they like ice cream. And sometimes the answer is both yes, and sometimes both say no. What's going on here? They somehow know the other twin is being asked this question, so they change their usual answer so as to be in agreement with their twin sister. But how is this possible? They know nothing about what is happening far away where the other twin is, and they are asked the question simultaneously, so there's no time for information to travel to the other twin. It's as if somehow they are telepathically connected to each other and know what each other is doing and thinking. Well, these twins are an analogy for measurements made on a pair of electrons. The electrons would be produced simultaneously and then leave in opposite directions, just like the twins did. But instead of asking the electrons, "Do you like ice cream?" we make measurements of each electron's spin state. And the bottom line is that when the same type of measurement is made at the same time on each electron, the results are different than when measurements are randomly made on one or the other electron. The description of the electrons and the analogy with the twins is a bit of a simplification, but the idea still holds, and it is absolutely stunning. How can we interpret this? It seems as if the electrons are still connected to each other, even though they are separate. There is no time for information to get from one electron to the other so as to communicate what the results should be. But they somehow know that they are both being measured at the same time, and they adjust their spin states accordingly. The only way we can understand this result is to consider that the separated electrons are somehow entangled with each other, hence the term quantum entanglement. By that we mean space is somehow connected so that even though one electron is here and the other is over there in the normal sense of those terms, they are still right together. In a sense, we have lost the idea of location, hence the term non-locality. This paradox is truly amazing. It's known as Bell's theorem and has challenged our thinking of the physical world since this idea was first discovered in 1964 in a paper by John Stuart Bell. And at the bottom there, I give you a few terms that you could Google if you want to read more about this. Well, I hope you agree with me that God's creation is indeed wonderful and mysterious. Again, as asked in Job, can you fathom the mysteries of God? Can you probe the limits of the Almighty? Folks, I've enjoyed spending a semester with you. I hope that you had a good and worthwhile time in my class and you learned a lot and you're eager to build upon that newfound knowledge.